we have a circle and we have some lines tangent to the circle. What that means is lines just basically touching a circle. They can't help but be tangent. This means that they are perpendicular to the radii of the circle. When we talk about circular motion, we're talking about an object going in a circle, which means its velocity is constantly tangent to that circle. So in this case, the velocity of an object could be, 2 meters per second. So the speed of that object is said to be constant because speed is non-directional, but the velocity is constantly changing. Because acceleration is a change in velocity over time, even though the magnitude of the velocity is not changing, the direction is. It's constantly changing. So we say that we have a centripetal or center-seeking acceleration. Our formula for centripetal acceleration is v squared over r. The net force of an object going in a circle would be its mass times v squared over r. The net force of something going in a circle is sometimes called the centripetal force, but this can be very confusing. When we have an object going with a centripetal force, we don't have a new force in the universe. We still just have the four forces we've always had. We have the strong force and the weak force. Those are both nuclear forces that exist between particles in the nucleus of an atom. The other two are gravity and the electromagnetic force. There's no fifth force. There's no centripetal force. So when we're talking about a centripetal force, we're talking about either gravity or the electromagnetic force or some combination of both. Let's take an example. Let's take the example of the moon orbiting around the Earth. So here's the Earth, here's the moon. The moon has a force on it. The only force on it is the force of the Earth's gravity. And the moon is traveling with tangential velocity around the Earth. So the net force causing the moon to accelerate is the force of gravity, the Earth's gravity on the moon. So the force of gravity equals mv squared over r, and r in this case is a very long distance from the center of the moon to the center of the Earth. Let's do another example. Let's do a horizontal example, a car going around a circular road. So when the car starts going in a circle, there must be a force making it go to the center. It's the friction. It's the static coefficient of friction times the normal force, the friction of the car's tires on the road, causing it to go in a circle. F net equals ma, so the net force is the friction force. Let's look at a force diagram. We have the weight of the car down, the normal force up. They're balanced. The friction force is not balanced. It's why the car is going in a circle. So if we do F net equals ma, we have the friction force, which is the normal force times the coefficient, equals mv squared over r. In this case, the masses cancel, and we could find the velocity to keep the car on the road. It's the square root of g times the coefficient of friction times r. Vertical circles are a little bit different. Here in a vertical circle, we're taking a cork on the end of a string and we're whipping it around in a vertical circle. We're going to look at the forces on 4 different locations, the top, the middle, and the bottom. And in each case, we're going to do F net equals ma, or in the case of circular motion, F net equals mass times the centripetal acceleration. In the case of the top, we have 2 forces. We have the weight of the cork, and we have the tension in the string. I'm purposely showing them not to be the same. But both of them added up provide the force to make the cork go in a circle. So we can solve this for the tension equals mv squared over r minus mg. It's different when we get to the middle. When we get to the middle, only the tension is pointing towards the center of the circle. The weight is actually pointing to the center of the Earth like it always does. Because there's no component of the weight going toward the center, the tension is simply equal to mv squared over r. It's what's causing the cork to go in a circle. When we get to the bottom, things are different again. The tension is going to be the only thing making us go in the circle. The weight is actually trying to make us go out of the circle. So we have the tension minus the weight equal to mv squared over r. So note that the tension is mv squared over r plus mg, considerably higher than either of the other two cases. And finally, if you got into a case where you're somewhere in the middle, then you would have to break the weight into components, one of those components going towards or away from the center of the circle.